Let's take a look at binary shifts. The two main types are logical shift and arithmetic shift, whereby we are basically moving bits either to the left or to the right by a given number of time. Now that means with a logical shift, we have the logical left shift as well as the logical right shift. The same applies with the arithmetic shift. We have the arithmetic left shift and the arithmetic right shift. Now, before we dig into examples, note that the logical left shift and the arithmetic left shift, they're basically the same. So as we progress with our tutorial, we won't be talking about the arithmetic left shift. Let's start off with the logical left shift. Now, basically with the logical left shift, as the name implies, we are moving the bits to the left in a register. Look at this example. This one is a string of 8 bits. Now, with binary shifting using the logical left shift, we are moving all these bits from the left to the right. Now get this, this one is the most significant bit and this one is the least significant bit. Now with the logical left shift, we are mostly concerned with what happens to the most significant bit. Let's look at this example again. This statement says the most significant bit is discarded. Let's start. We have the 1 and it moves here. We have the 0, it moves here. We have the 1, it moves here. As we progress, you realize that when we are at 2 to the power 7, the 0 is moved to this one. Now this bit does not have any slot to be fitted in. Now this one is the most significant bit that is being described by this statement there. And if this most significant bit is discarded, in other words, it's lost. Now when the most significant bit is lost, if we go back to this one, you realize that we now have a string that is 0 1 1 0 1 0 1, but these are 7 bits, but we originally have 8 bits. So we now have a 0 that is added to the right there to make it 8 bits. So pretty much that's what happens with the logical left shift. Let's look at another example. This time we're moving to the left 2 times. Let's see how that goes. So we have this one, it moves 1 and 2 and it's now here. We have this 0, it moves 1 2 positions and it's now here. The same applies. We have this one bit, it moves 1 2 times and it's now here. You do the same until you reach this bit here. Now you get to realize that if I move this bit 2 times, I will be moving it to the left for the first time and then the second time, and it means my register is now full as far as I'm concerned, though I would be having empty space here. Now that means all these other bits, they are not going to be moved anyway, so they're going to be discarded. You understand? But these empty spaces that were created after this movement, we now replace them with 0. Let's look at the last example for logical left shift. Now with this example again, we're moving it, the bits 4 times. So pretty much the same as we did it before, but to put things in perspective, let's go along together. We move this one, this 0, 1 2 3 4 times, and this 0 is now landing here. The same applies. We move the 1 4 times, 1 2 3 4 times, and this one now lands here. Now you do the same until you arrive here. Now you realize that when we get here, I'll move this bit 1 2 3 4 times and I land here. Now let's see what happens if I try to move this one 4 times. I'll move it 1 2 3, but then when I move for the 4th time, I have no place to place that bit in my register. So that means starting from here, all these 4 bits are going to be lost. But then at the same time, when we have 4 bits that are lost, we also have originally empty 4 spaces that are to our right. So those empty spaces, we add zeros. Now, to make it interesting, when we are moving to the left, the number of times we have moved determines the numbers of zeros that we are putting to the right. In this case, we are moving to the left 4 times. So that means I have I'm moving to the left 2 times, and that means I have 2 zeros that I'm going to be putting to the right. Here I'm moving to the left 4 times. That means I have 4 zeros. The same applies with the previous example. Now, let's move on to the logical right shift. Now, the logical right shift is pretty much the opposite of the logical left shift. So if you mastered the logical left shift, you should be able to go through the logical right shift. Now, let's start with this example. As usual, in our 8-bit register, we have the most significant bit, which is the leftmost bit, and then we have the least significant bit, which is the rightmost bit. Now, you get to realize that with the logical left shift, the most significant bit was the one that was being discarded. But in this case, we are discarding the least significant bit. But that's just something we figured out. But let's see how that happens. When I'm moving to the right, I'm supposed to note how many times I'm expected to move to the right. In this case, I'm expected to move 1 time each bit to the right. So when I move this bit 1 time, it lands here. When I move this 0 1 time, it lands here. When I move this bit 1 time, it lands here. Now the same goes for the rest of the bits. Let's look at the 0. When I move this 0 1 time, it lands here. But then when I have this least significant bit that is being talked about by this statement, the least significant bit, when I'm trying to move it 1 time, I have no place in my register to store it. So that means this one, it's lost. But as much as I have lost the least significant bit, I have also created an empty space here that will make my register amount to 7 if I don't have any bit here. So in this case, this empty slot is replaced by a 0, whereby we say a 0 is added to the left. This is the 0 that is added to the left. With the logical left shift, we were adding the 0 to the right, pretty much the opposite. Let's look at another example. In this example, I'm moving to the right 3 times this 8-bit number in an 8-bit register. Now let's see. When I try to move this 3 times, I move the 1 time, 2 times, and the 3 times, and it lands here. I move the 0 1 time, 2 times, and 3 times, and it lands here. Now I can do the same for these ones, but let's try to look at what happens here. When I move this 1 time, 2 times, 3 times, it now occupies the rightmost part and fills our register already to the right. That means we have no slots to add more numbers. Let's now look at this one now. If I try to move it 3 times, I will move it 1 time, 2 times. The 3rd time now, there is no slot that I can store it in. There is no index that is available for me to store. So that means the same applies for this 0, the same applies for this 0. They don't have any place to be stored, so they will be discarded, right? But as much as we have discarded these 3 rightmost bits, right, we also have empty spaces that are created or left available, but they need to be stored. Otherwise, our register will only have 1, 2, 3, 4, 5 bits. So these empty slots, I put 3 zeros. Now to put in perspective, like we talked about, the number of shifts that you're performing determines the number of rightmost bits to be discarded, and then the number of zeros that needs to be filled. So in this case, these ones becomes our least significant bits, so each time they are discarded. Now let's look at the final example, and we are moving this one 5 times. Now pretty much I guess you understand. Let's start with the concept. I'm moving 5 times to the right, so I'm expecting 5 bits to be lost. 1, 2, 3, 4, 5, and I'm expecting 5 bits to be replaced, 5 slots to be replaced with 0. 1, 2, 3, 4, 5. So pretty much we're saying I've moved this one 1, 2, 3, 4, 5, so it's now here. I moved this 0 here 5 times. 1, 2, 3, 4, 5. It lands here. I move this one 1, 2, 3, 4, 5. It now lands here, and obviously this becomes our new string. Let's look at the arithmetic right shift. Now of course we are supposed to talk about arithmetic left shift, but the arithmetic left shift is similar to the arithmetic right shift. So what we did in the arithmetic left shift is basically what is going to be done in the arithmetic left shift. But let's look at the arithmetic right shift. Now with the arithmetic right shift, the concept is the same, of moving bits to the right, because we are performing a right shift, but the idea is different, because when we have this string here, the most significant bit determines the sign. That is it a positive number or a negative number? Now when we have a 1, it means this one is a positive number. When we have a 0 as a most significant bit, it means this number will be a negative number. Now the idea with the arithmetic shift, right shift, is that we need to maintain the sign of the binary value that we have. That is, if it's a positive, after the right shift it's supposed to remain positive. If it's a negative, after the right shift it's supposed to be a negative. Now let's explain to what happens there. So first and foremost, when you are performing the right shift, you look at the number of times you're supposed to perform the right shift. In this case, I'm performing the right shift 1 time. So this bit here, it moves here. This one, it moves here. This one, it moves 1 time here. This one, it moves 1 time here, until I'm done with all these other bits. Now when I try to move this one here, you realize I don't have any space in my register to store this one, so obviously it's discarded like what we were doing before. But then this concept is the same throughout except for this part. Now what happens is this: if the most significant bit was a 1, obviously there was an empty slot that was created during our right shift. So in that empty slot, we then find out what symbol the most significant bit was representing. That is, was it a 1 or a 0 to represent a positive or negative? So if it was a 1, we retain the 1. But if this value was a 0, we'll retain the 0. And our result, of course, will be 1, 1, 0, and this string here. Now let's look at a different example. Now, obviously, there are short methods and long methods. Now in this case, I'm going to be moving 2 times to the right, performing an arithmetic shift. This bit here, it's moved 1 time, 2 times, and it lands here. The 0, it moves 1 time, 2 times, and it lands here. Obviously, we do the same. This one here now, we move. You understand this concept, so all these numbers are going to be moving, but let's now jump to this part. This one moves 1 time, 2 times, and it lands here. Now since this one is landing at the rightmost part of our register, it means that we don't have any space to store this 0 and this 1. So obviously these ones are discarded. You understand that, obviously. But let's talk about the signs. We are performing an arithmetic right shift 2 times. Now that means when I have created 2 slots that are empty, I'm supposed to retain the value of the most significant bit. So in this case, I retain a 1 in this slot and I retain a 1 in this slot. Suppose this one was a 0 again, you retain a 1 in this, a 0 in this slot, and you retain another 0 in this slot. That's pretty much how the arithmetic shift goes. So it means that if I'm shifting this bit 3 times, obviously I'll have a 1 and a 1 and a 1, right? If it's 4 times, I'll have a 1 and a 1 and a 1 and a 1. You understand? Now, for interest's sake, let's try to look at the long method. Now this is the long method, all right? So you realize, Kuti, you realize that this result here is supposed to be the same result in our final answer, which is this one. So you can understand that once I perform the right shift once for this string here, I have moved this one time, I've moved this one time, and performed everything and retained the most significant bit as my signed value here. It means I now take this string and now perform another shift for the second time. So 1 1 0 1 1 1 0 1 1 0 1 0 1 0 1 0. So it's pretty much this one. I'm now performing another shift, and obviously I'll have a value. Now let's look at it. 1 1 1 1 1 1 and then 0 0. So this result and this result are the same. So if you are not good with this first method here, you can obviously work with the second method. Let's try another example. I'm moving this one 4 times. So it means now this one is a negative value. So you can tell what I was talking about before. I moved this 0, 1, 2, 3, 4 times, and I move it here. The same applies. I'll move the 1 and the 0. Now let's move the 1 here. I'll move it 1, 2, 3, 4 times, and I land here. Now that means these bits have no space again, so they're discarded. But then also I have empty slots here. Like what we talked about, we retain the value of the most significant bit for all the slots that exist. So if you have 5 slots, you have 5 zeros. If you have 6 slots, you have 6 zeros there. The long method pretty much goes the same. You perform the first shift, that is, you perform one shift to the right, and then this result you perform another shift right now, and then you have this one, and in this result you perform another right shift and you have this result, and this result you perform the 4th shift and you have this result. So I have 0 0 0 0 0. Let's look at the previous one. I have 1 2 3 4 5 zeros, so it's correct. It's similar to this solution there. Now with cyclic shift, we have no bits that are lost. Now that means the ones that are discarded, as we were talking about them in the arithmetic and logical shift, in this case we don't actually discard them, but we perform a cycle whereby they go back to replace the ones that were empty. That means the slots that were empty. Let's demonstrate this with an example. Now let's look at this example whereby I'm supposed to move these bits 1 time to the right. Now that means when I move the 1, it lands here. I move the 0, it lands here, and I move these ones, they still move 1 point to the right. Now let me move this one. If I move the 0, it lands here, right? But when I move this one, it pretty much doesn't have any place to be stored in the rightmost part of the register. But in this case, we now perform a cycle whereby it now lands at the very first spot that was created, that is available, and it becomes the most significant bit. So that means we have performed a cycle whereby instead of discarding this, like in logical shift and arithmetic shift, in this case we are now bringing it back to become the most significant bit. Let's try another example. I have this register where I'm supposed to move these bits 2 times to the right. As usual, I then move this one 2 times, it lands here. I move this 0 2 times, it lands here. Now I will do the same for the rest, and let me move this one now 2 times, it lands here. When I have the 0, I will move it 2 times as well. 1 time, 2 times. Now in this case it doesn't have a rightmost slot for it to be stored, but then I perform a cycle and it lands on the very first spot and becomes the most significant bit. Now I go back, I'm left with 1 bit here, which is a 1 that I haven't moved, so I move it 2 times again, but then obviously I cannot move it any place to the right. Now I perform another cycle and it goes back into the register and becomes the value at 2 to the power 7 in the register. So pretty much you can do this for cyclic shifts of 3 positions, 4 positions. It just means that when you have the values to be moved or the number of times to be moved, it means that you're going to be having 2 bits that are going to perform a cyclic shift back into the register. When you do that, you're done.